Hello everyone. In the last session, we have discussed about Cartesian sign conventions. Using those three rules, now I am going to derive relation between focal length and radius of curvature. As we already know that focal length is distance between pole and principal focus, and radius of curvature is distance between pole and center of curvature. Now here I am going to consider concave mirror whose reflecting surface is towards the center of curvature, and this concave mirror gives real and inverted image. So here either we can consider concave mirror or convex mirror, so we can get the same result, that is relation between focal length and radius of curvature. Now here I am going to consider concave mirror, only the reason is we can get real image and converging of light takes place after reflection. Now you can observe this ray diagram. This XY is aperture of concave mirror. When light falls between the area X to Y, reflection of light takes place. Then P indicates pole. Pole is midpoint of spherical mirror. And C is center of curvature. This is center of sphere of which spherical mirror is a part. Then R indicates radius of curvature, that is distance between pole and center of curvature. Now I am going to consider a parallel ray of light, that is LM. This parallel ray of light is traveling parallel to the principal axis and it is going to fall on the concave mirror at point M. This is point of incidence. When a ray of light falls on concave mirror, a part of light is turning back to the same medium. Now you can observe this reflected ray is passing through the principal focus because this is concave mirror. After reflection, converging of light takes place. Now LM is incident ray, MF is reflected ray. Now I want to measure angle of incidence and angle of reflection. Angle of incidence means the angle between incident ray and normal. So we need normal here. So now let us draw the normal. This dotted line indicates normal. Normal is passing through the center of curvature. Let us draw normal. This is passing through center of curvature. Now easily we can measure angle of incidence. This is angle between incident ray and normal, and angle of incidence, let us take it as theta. Then similarly, angle of reflection. Angle of reflection means angle between reflected ray and normal. Reflected ray is MF, normal is MC. So we can take angle of reflection is also theta. This is according to second law of reflection. According to second law of reflection, we know that angle of incidence is equal to angle of reflection. Theta and theta both are equal. Now I am going to draw the line MD. This line is perpendicular to principal axis and also it is very close to pole. So here I am going to draw this reference line or this line which is perpendicular to the axis. So this line I drawn only to measure the angle because this is not a plane mirror. This is a spherical mirror. It is very difficult to get the angle. Only for that reason we are going to draw the line MD which is perpendicular to principal axis and also very close to pole P. Then F indicates focal length, that is distance between pole and principal focus. So this is all about ray diagram. Using this ray diagram, now we can derive relation between focal length and radius of curvature. We can observe the points here. In that ray diagram, LM indicates incident ray, MF indicates reflected ray, CM indicates normal, which is passing through center of curvature, MD indicates the line perpendicular to principal axis and also very close to pole, P indicates pole, F indicates focal length, R indicates radius of curvature, C indicates center of curvature, and XY is aperture of concave mirror. Yes, from the diagram, angle of incidence and angle of reflection both are equal. That is, according to second law of reflection, we can write that angle LMC and angle CMF. LMC, CMF, angle of incidence is equal to angle of reflection. So we can write that angle LMC equal to angle CMF equal to theta. Both are equal to theta. There are two alternate angles in the diagram. That is, you can observe angle LMC and angle MCD. LMC, MCD, these are alternate angles. When angle LMC is theta, then angle MCD is also theta. So angle LMC equal to angle MCD equal to theta because they are alternate angles. So one more alternate angle you can observe in the diagram, that is angle LMF. So angle LMF, the total angle is 2 theta because theta plus theta becomes 2 theta. Then angle LMFD, LMF is 2 theta. Similarly, angle MFD is 2 theta. This is again one more alternate angle. That is angle LMF equal to angle MFD equal to 2 theta because they are alternate angles. From the diagram, you can observe the triangle MCD, angle MCD and angle MFD. Angle MCD is theta and angle MFD is 2 theta. Now we can easily find tan theta here. Tan theta is opposite side divided by adjacent side. So from the triangle MCD, tan theta equal to opposite side is MD divided by adjacent side is CD. So from triangle MCD, tan theta equal to MD divided by CD. Let us take it as equation number 1. Similarly, one more triangle, that is triangle MFD. Triangle MFD, here we can easily find tan of 2 theta. Tan 2 theta equal to again opposite side divided by adjacent side, that is MD divided by FD. So from the triangle MFD, tan 2 theta equal to MD divided by FD. Let us take it as equation number 2. So I am going to consider paraxial rays in this ray diagram. So what are paraxial rays? The rays which are parallel and very close to principal axis. When we considered paraxial rays, angle is very small. You can imagine if this line LM, if it is very close to principal axis, automatically angle of incidence and angle of reflection becomes very small, so that alternate angles theta and 2 theta becomes small. To get the smallest angle, we are going to choose paraxial rays. So here for paraxial rays, theta is very small, so here we can neglect the trigonometric functions. That's why you can observe equation 1 and 2. In equation 1 we have tan theta, in equation 2 we are having tan 2 theta. So tan is neglected because theta is very small. So why theta is very small? Because we considered paraxial rays. What are paraxial rays? The rays which are very close to principal axis and traveling parallel to it. So tan theta becomes theta and tan 2 theta is equivalent to 2 theta. Therefore, equation 1 and 2 becomes, here tan is neglected. So theta equal to MD by CD. Let us take it as equation 3. and equation 2 becomes 2 theta because here also tan is neglected. So 2 theta equal to md divided by fd. Let us take it as equation number 4. That means now we got the value of theta and 2 theta. Let us divide these two equations, dividing equation 3 by 4 so that we can get 2 theta divided by theta equal to md divided by fd divided by md divided by cd. So when we divide these two equations, md will get cancelled. So it becomes cd divided by fd. So here theta will get cancelled. So 2 equal to cd divided by fd. Let us take it as equation number 5. Now you can observe the point M. When we considered paraxial rays, this ray of light is very close to principal axis, so that M is very close to P. When M is very close to P, then the point D is also very close to P. So here we are going to consider this D is equivalent to P because D is very close to pole. Now I am going to consider, instead of taking CD, I am going to take it as CP. CD is equivalent to CP because this D is very close to pole. So we can write CD is equal to CP. Then here, what is the distance between CP? C indicates center of curvature, P indicates pole. The distance between pole and center of curvature is called radius of curvature. So instead of writing CP, we can write R. Then similarly, the next point is FD. Again, instead of FD, we can take FP because again D is very close to pole. So we can consider FD is equivalent to FP. And what is FP here? The distance between pole and principal focus, and this is called focal length. Now, in place of CD, we can write CP. In place of FD, we can write FP. Then CP means R and FP means F. So we can get 2 equal to R divided by F. This equation number 5 can be written as 2 equal to R divided by F. But you can observe here, I wrote a negative sign, that is only because of Cartesian sign convention. You can remember the 3 rules of Cartesian sign conventions here. All the distances are measured from the pole along principal axis. Now, I am going to measure a radius of curvature. Radius of curvature, that is from pole to center of curvature. Pole to center of curvature is exactly opposite to the direction of incident ray. Incident ray is moving in forward direction, but we are measuring radius of curvature in backward direction. When it is against incident ray, then we have to take it as negative. Similarly, focal length, that is distance between pole and principal focus. Pole and principal focus, this distance is also against the direction of incident ray. So if it is against the direction of incident ray, again it is taken as negative. This is according to Cartesian sign convention. Equation 5 becomes 2 equal to minus R divided by minus F. So negative sign get cancelled. So this equation can be written as F equal to R by 2. So F equal to R by 2 indicates that focal length is always half of radius of curvature. This is the relation between F and R. Or we can also say that radius of curvature is twice the focal length of spherical mirror. In this derivation, I considered concave mirror. So if you want, you can take convex mirror also. Again we can get the same result, that is F equal to R by 2. But here I considered concave mirror, only the reason is we can get real and inverted image, and also converging of light takes place after reflection. So for that reason I considered concave mirror. So the relation between focal length and radius of curvature is F equal to R by 2. That is, focal length is half of radius of curvature. So this derivation carries 3 marks.